Hello. Now I'm going to talk about another one of the methods that we use to find the roots of an equation. In this case, it's the Newton-Raphson method that is characterized as an open method. Um, this is because, unlike the bisection method that's categorized as a bracketing method, it doesn't bracket the root of a function between two intervals. So, because of this, it's actually pretty cool because since we don't have to bracket the root, we don't need two initial guesses. We just need one, which makes this method a lot more common because you only need one guess. In this case, we're gonna call this guess xi. And so the way that it works is that this method extends a tangent line at the point xi, at the function evaluated at this point xi. Um, and this point where the tangent line crosses usually represents a good estimate of the root. And although, since this is an open method, it's important to point out that sometimes, depending on the function, it can converge and then all of a sudden it's diverging. With the number of iterations, it could eventually come back and converge again, but it is normal to see some change in error between each of the iterations. However, it is a lot like once this method converges, it's quicker than the bracketing methods. So, and the reason why I think it's kind of cool too is because it bases off everything from the derivative of a function. And the reason why this method uses a derivative obviously is because it's the slope of this function. Okay, so I'm gonna go ahead. So this is basically how it works, um, like the overview. And now I'm gonna show you my code. Um, since we were actually gonna use the derivative, we had to like find how to establish the derivative of a function here on MATLAB. And this is the way I am solving for this function here, which is, I believe, the first problem, 6.1 of our textbook. And then this is the derivative of this function. Um, we have our initial guess x0, which is the one that I mentioned, xi. Then we go ahead and repeat this process from 1 to 100 iterations. Usually it ends sooner. This is more MATLAB um, like jargon. It just means that the function is evaluated at that point, and then that the derivative is evaluated at that point. Then we go ahead and use this, which is the equation of Newton-Raphson, which is that initial guess minus the function evaluated at that point divided by the derivative of that function evaluated at that point. We go ahead and let this run, and it finds the root of the equation. So I'm going to go ahead and try to run it here. So it's going to be like enter number of decimal places, like how precise we want an answer to be. I'm just going to go ahead and put 6, not a big deal. The initial guess of this problem is 3, which is given by the book. And then it gives us the answer, which is right here. The root is 3.56. On our final delivery, we went ahead and estimated the root for 3 different equations, which is this one, a trigonometric function, just to see, with an exponential there, and it worked. And then this last one, which is another polynomial. It's actually quite cool. Then I just want to go ahead and talk about some of the errors that could happen from working with this Newton-Raphson method. And yeah, I'm going to use this picture here. Basically, since the Newton-Raphson works with the derivative and the tangent line that extends, usually there's problems when there's an inflection point. That means when the second derivative is equal to 0 here, right here, there's a change, there's an inflection point, which might also cause lots of error there. Another reason for error occurs when we reach like a non-zero slope over here. Obviously, that's a problem because when you reach a zero slope, that means that the derivative of the function was zero, and dividing by zero is a mistake there. Another reason for error here that could happen is when the initial guess is close to the root. It can make it like go crazy over here. And finally, another one is when the tangent line obviously doesn't even make sense because it's not even crossing. And that'll be all for this method. Thank you.